Well, thank you for coming again. So, the purpose of these lectures was to make you appreciate, I think we should request the head of the department to put carpets. So the purpose is to appreciate why quantum mechanics is important. That's why. And in the last lecture, I explained how important things like lasers and understanding of quantum optics and the behavior of elementary particles, these are all governed by quantum mechanics. And I also said that the applicability of quantum mechanics is like an ocean. Even if I lecture you for years, I can't bring everything in. So that's not the idea. Anything that you do, nuclear physics, materials, chemistry. Now people are even talking about biology, which is not surprising because deep down, biology is coded in big molecules like DNA, and somewhere quantum mechanics will play a role. Photosynthesis, when light falls on a plant, it converts that energy, converts light into energy. It's quantum mechanics. Okay, so therefore I have to be selective. And today I want to talk to you about another amazing phenomenon called superconductivity. Okay? And I'll explain to you what is superconductivity. I cannot do I can't do any justice as to why quantum mechanics explains it, and why quantum mechanics is central to it, because that's somewhat technical. But it's true that without quantum mechanics, there is no way of understanding superconductivity. Now, superconductivity, again, like lasers, bridges two different worlds. On one hand, it has amazing technological applications. On the other hand, understanding it requires going deeper and deeper into the foundations of science. So that's a very good example. But what is superconductivity? We tend to use big adjectives like super very easily, You go to some restaurant and you say, oh, that was super, Till next day you go to another restaurant, find that was more super than this one. So why do we call it superconductivity? To appreciate that, let us understand what conductivity is. I'm sure all of you know what conductivity is, but I will again start at the basic. This is the inverse of resistance. And resistance, even in our normal usage, says something is opposing. So in this case, something is opposing currents. So we take a piece of metallic wire, so we all know what's the metal and what is not a metal. This is not a metal. This is wood, okay? It doesn't conduct electricity. It may conduct very, very little, but by and large, if I connect a battery to 2 points here, there'll hardly be any current. On the other hand, if I take this and take 2 points, connect it to a battery, current. So there are metals and there are insulators, and then you can go on. There are semiconductors, etc. Even this basic distinction between what is a metal and what is an insulator, you need quantum mechanics to understand. Okay? But roughly, a metal is one where inside which the electrons behave as if they are free. As if they are not really free, because the electrons in this, if they were free, they would have come out and gone wherever they wanted. They are not free. But they're inside, they're as if they are free. Inside this insulator, they're all bound. Everything is made up of atoms, and the electrons are the ones that carry currents. And in an insulator like this, they're all bound to the atoms. But in a metal, some of them, they lose their attachment to the atoms and they're freely wandering inside the metal. So I take a piece of metallic wire and connect it to a battery. This sets up an electric field along the wire, and electrons being charged particles will be accelerated by the electron. So if I blow up this wire, so you see, so this is the direction of the electric field, and actually I should take, okay. Then the electrons being negatively charged, they will be accelerated in the opposite direction. If nothing stopped them, then they would flow. But there are a lot of things which are scattering these electrons. They are positively charged ions, sometimes electrons themselves, they scatter. Scatter means if an electron is going like that and it hits another electron, it can get scattered away from the direction. So the net motion is reduced. It's as if there is a resistance to the flow of electron, and this is resistance. And when there is a lot of resistance, not much current is conducted. So conductivity is low. When there is not so much resistance, there is a lot of current flowing and conductivity is high. And that's why I have conductivity inversely proportional to resistance. So this is how we understand that. And these are very classical. You didn't really need quantum mechanics for that. And to understand this, even our day-to-day life is, you go to some crowded part of the city like Sayajirao Road on some special day, and you see everybody is milling around. It's very hard to walk without bumping into somebody, and the bumping is like scattering, and your motion is reduced, sometimes you can't move at all. So this is what is happening for electrons here. That's conductivity. But what is superconductivity? Thank you. ಇದು ತಗೊಂಡೋಗಿ ನನ್ನ What about you? What about them? I feel shy to drink tea. We are brought up to say that we should share everything, but I don't want to offer this to you. So, superconductivity is this amazing phenomenon found in 1911 by the Dutch physicist. His name is Kamerlingh Honest. Some people say it's actually a student who discovered it, because big professors, they hire a lot of students, and the student's job is to turn on the power and keep watching something when the professor is, having some nice drinks and eats with his colleagues. And then at the end of the day, they ask the student, what the hell have you been doing? And the students try to say, I did this, I did that, and the professor doesn't listen, because most of it is not interest. The student will say, when I watched the thermometer, and it was always then, in the evening, the reading went down, and at noon it went up. Okay, this is data. Most data is boring. But you should be careful. If somewhere something happens, and there is some breakthrough. So Kamerlingh Honest comes and asks the student, what did you do? This student is supposed to have taken mercury and cooled it to very low temperature. Below that. And when you don't know what's happening, you make all kinds of measurements. So, Kamerlingh Honest's student was measuring current flow, this, that. He had already cooled the sample to a very low temperature, and then he was supposed to watch what happens to resistance. But like all students, they're very tired and they work the whole day, and this student is supposed to have fallen asleep, and somewhere along the line, the temperature of mercury went up a little bit. And the student noted that suddenly the resistance had gone up. Actually, he should have noted the other way around. He should have noted what happened when the temperature was lower. And in fact, what happened was that the temperature, there's some fall here, suddenly drops to 0. But there is no such thing as 0 in physics. When you measure, you'll always find some small fluctuations, error due to the meter. So as they improved the measurement accuracy, they found that the resistance was 0. No matter how precisely they measured, resistance had become 0. So conductivity became infinite. There is something called perfect conductor, which is not the same as superconductor, And I can't go into that detail, but if you're interested, you should look it up. No, this was a shocking discovery that resistance actually went down to zero. So what happened to all this theory that they're always scattering and resistance should always be there? There was no resistance to the flow of electrons below 4.02. That was a major discovery. Before trying to go further, let's understand the implications of it. If there is no resistance, then when you take a wire and send a current, the wire heats up, which is basically the energy dissipated in all these collisions. And that is called ohmic heating, because this is Ohm's law, which says the voltage is current times resistance, and there is a power loss. Now, if there is no resistance, then there will be no power loss. So you can transmit currents if you could build a huge superconducting pipe without any loss, transmission losses. That will be a fantastic savings, very efficient way of transmitting current. So this idea, 1911, more than 115 years ago, has been an area of very intense research, in particular to see if we can get this phenomena at higher and higher temperatures. Why? Because if you can only get superconductivity at very low temperatures, you have to cool the sample. That takes a lot of energy. Okay? It's expensive to cool. I don't even know whether on this campus there is a cryogenic facility. Okay? But if you can achieve a superconductivity at room temperature, then you have the advantage of no resistance and no disadvantage of cooling and all that. So you keep hearing all the time, high temperature superconductor, it has been found, it has not been found, etc. But the day it is found, it is going to transform our living in some amazing ways. Those are the technological aspects of that. And I'll come to more technological aspects of that. But before that, I must tell you, so how is the superconductor defined? When do you know that you have observed superconductivity? One is for the resistance to go to zero. There is another phenomenon which is equally fundamental. And to understand that, suppose I take a ball of superconductor but I have not cooled it yet. And I put it in an external magnetic field. So the magnetic, hey, this looks white to me. So sometimes saffron can be white also. Okay? So you must learn the deep message behind that. And both are the same, that's no good. Now let's see in Mysore University, blue also looks white. Oh no, it doesn't. So here is how the magnetic field lines will look. When T is above the critical temperature. This is called the critical temperature because something critical happens at that time. Now you cool it. Cool the sample below T. what happens? There is a superconductor. Very far away, the magnetic fields are unchanged, but magnetic fields that went through the superconductor earlier are completely expelled from the superconductor. So inside the blue superconductor, the magnetic field B is zero. Now, this is another amazing phenomena. And I don't know how much electrodynamics you people have learned. There are many different kinds of magnetic fields. There's a B, there's an H, etc. It's only the B field that vanishes inside a superconductor. You say, okay, so what? Well, what am I supposed to do with this? Nothing. Now I do a cute experiment. I take a ring of superconductivity, and I do the same experiment. I put a magnetic field, cool it, then the magnetic field is completely expelled inside the ring. So the magnetic flux inside the passing through the ring changes. And when the magnetic flux changes, there's an EMF set around the ring, and a current is set on it. Now, after you cooled it, there is no change of flux, there is no EMF, there is still a current. So you have a current flowing through the superconductor with no EMF. And if I had done this with a wire, I set up a current and suddenly disconnect the battery, very quickly the current dies off because this resistance takes over and the current goes to zero. But now there is no resistance because it's a superconductor. So this current will go on flowing without any resistance from outside. You don't need a battery to maintain this current. And this is called a persistence current. Now, what's the Kannada word for persistence? What is current in Kannada? Vidyut. That's electricity. We need a word for current because we talked about communication. So, persistent means something that is persistent. Like a child is persisting to get that biscuit and the parents don't want it to eat so many. So, adu mondutana. So, ಈ ಕರೆಂಟು ಮಗು ಥರ ಮೊಂಡು ವಿದ್ಯುತ್. You'll be surprised to know that the longest persistence current is estimated to last 300,000 years. Okay? And you can increase it depending on your accuracy. So, you see, this superconductivity has some magical properties. And I'll describe one more of that. I take a superconducting ring. In fact, what would be a Kannada word for superconductivity? Okay. So now I'm training you to become future communicators of science in Kannada. So you have two homework. Persistent current, you must find a good Kannada word. Mandutana, etc. will not work. Okay, we need something that sounds like science and not the way some parents are complaining about their child. Okay? And superconductivity. Now here comes experiment. In almost every science fair, you will see this. So here in the superconductor, you must cool it, of course, and you take a magnet, like a small cube. If this is not superconducting, the magnetic field of this magnet would be going everywhere. But the moment it becomes a superconductor, no magnetic field can go through here. And the way that is achieved is persistent currents are set up in the superconductor to exactly cancel the magnetic field that would have penetrated. But those currents will produce a magnetic field here, which can either attract or repel the magnetic field, magnet. And with some homework, you can show that the magnet actually is repelled. So the magnet floats, and this is called levitation. Our yogis are supposed to have done this, they just sit and they say Om long enough, and suddenly they're airborne, At least that's the claim, and this is called some siddhi. And one very famous Indian physicist, George Sudarshan, we could never tell whether he was serious or joking. He went to Maharishi Mahesh University. He said there was a hall full of disciples, and after about 10 minutes, one by one they started taking off like planes in an airport and were levitating all over the room. And he said after about half an hour, the main problem was air traffic control because planes they can't go wherever they want. They will collide. So you read an air traffic controller who says, stay there, stay at that altitude, don't go in the direction. That's it. So these Maharishi disciples, they needed an air traffic control. Otherwise, I think it's a joke. But this magnetic levitation is real. I'm sure you can go and see a YouTube, and when you see it, it really blows your mind because, it happens. Now, if this could be achieved on a large scale, you can magnetically levitate trains. So they can zip past without any friction and all that and achieve amazing efficiency. So this is superconducting. And this effect is called Mysore effect. Actually, two people discovered it. One was called Oxenfeld, and those were scientifically conscientious. They call it Meissner-Oxenfeld effect. But in science, after a while, the name and the actual discoverers, don't have much connection. A may discover it, and the effect may be named after B. Some people say it shouldn't matter because it's the knowledge that matters. But if you are the guy that has been ignored, then it matters a lot because you lose recognition. Many times you lose money. You could have been appointed to as a professor somewhere, etc. So it's very important. So if you guys ever want to go into science, make it your first duty that you will give credit to previous work as carefully as you can. Okay? And it's not easy because you have to do a lot of literature search, but it's important. So this is superconductivity. It was discovered in 1911. But final understanding came only in 1957, what is called Bardeen-Cooper-Schrieffer theory, for which they got a Nobel Prize. And now this BCS theory is all quantum mechanics. So if you want to understand how superconductors work, you will need quantum mechanics. So let's see how we are going. We started 10 minutes late. So I will stop 10 minutes later. Only 20 minutes left. Not much I can do. But now I will try to explain what quantum mechanics. I have avoided mathematics so far. Because if you're not used to the mathematics, mathematics can hinder your understanding. But if you're used to the mathematics, mathematics can enhance your understanding. By and large, people are not as familiar with mathematics as they should be. Our mathematics education is very bad. We don't explain why mathematics comes in. Okay? So, when you do introduce differential equation, you say, why is it being introduced? Very important that whoever is teaching, whoever is writing books, must clearly explain why certain type of mathematics enters and why it's important and why so far that's the best way of doing it. Now the mathematics of quantum mechanics is hard to visualize, but I will try my best. So I will start with two-dimensional space. So I have two axes, and I look at vectors in two-dimensional space. A is a vector, and this is called a basis, and this is the unit vector in the x direction, and this is the unit vector in the y direction, and any vector can be written as a component along the x direction plus similar term along the y direction. We all know this, right? These are called basis vectors. They satisfy, and there is something called the dot product, which in this case is ax bx plus ay by. There's also something called the cross product. You don't have to go into that. And when you take this with itself, and that is called the norm of the vector, length of the vector. So the length of these two is 1, and the dot product between them is 0. Okay? Elementary. You might have learned it in your kindergarten, I don't know. And this is called a two-dimensional vector space. Now, if you want to change A by, let's say, rotating it to A prime through some angle theta, then you can relate the components in some formula, etc. This transformation is linear. Powers of components come in powers of 1. If ax prime depended on ax squared, then it would not be linear. So things like rotations are linear transformation. This whole algebra is called linear algebra. And you can write this in a fancy way. You can club these into a column and write this as cosine theta, sine theta, minus sine theta, cosine theta, acting on another column, ax, ay. The rule is you multiply this with that and add to it this with that. Okay? Then you can get this formula back. And this is called a matrix. And these are called vectors. So this is linear algebra, two-dimensional space. Everything is real. They're all describable by real numbers. But now I'll generalize this. Mathematicians, their greatest strength is they are good at generalizing it. They start with something and they generalize it to go to very, very general situations. And this leads to a generalization. You can stop anytime for questions, whatever you want. First generalization. Complex vectors. That means now all these components can become complex. Okay? And in this linear vector space, if I multiply A times A plus B times B and call it C, where A, B are real, I will still get a real vector. Now we generalize this. So instead of A, B, I can have multiply them by complex numbers alpha. Otherwise, the structure is the same. There will be basis vectors, there will be matrices whose entries will now be complex numbers. And this is called a complex vector space, and to keep life simple, we'll consider it for 2 dimensions. In vector algebra, there was no restriction on the length of the vector. Now I introduce a very special complex vector space called a Hilbert space. David Hilbert was one of the greatest mathematicians in Germany, and he developed this whole idea of a Hilbert space. This is still mathematics. You don't see any quantum mechanics yet. So I'm going to introduce a notation. Instead of calling it a vector, now I'll denote it like this. Okay? And I have to introduce something which gives me the notion of a scalar product, and that is called inner product, and that is represented by a, this is a complex number. Number is a number. Just as the scalar product was a number, and that was real. So you may say, fine, we can do it. So what? Correct question to ask. So what? The Hilbert space consists of vectors which are all of unit magnitude. So now vectors all have unit magnitude. That restriction was not put in the 2-dimensional vectors. Why do we do this here? You can do it. We can always consider a subclass of vectors that satisfies this, and there is no problem. Where does quantum mechanics come in? I am only describing. I am not really proving why this represents quantum mechanics. For that, you have to go study quantum mechanics. Before that, let's look at classical mechanics in 1 dimension. So, a particle is completely specified if you give me its position and its momentum or velocity at a given time. If you give me that, and you give me all the forces acting on that, I can tell you exactly what the position and momentum will be at a later time. You can either use Newton's laws, or if you are fancier, you can use Hamilton's equations, etc. So we say a state of a classical mechanical state is represented by xp, and you can imagine a space where one coordinate is labeled by x and another coordinate is labeled by p, and this is called a phase space. So we say state of a particle in classical mechanics is a point in the phase space. Okay? If you want, you can use this notation. Now, we say a state of a quantum system is represented by what? And this goes in a two-step process. This is sometimes not very well argued, but everything comes from physical reasons. This is not the way quantum mechanics was discovered. Schrodinger wrote his Schrodinger equation, and Heisenberg wrote everything in terms of matrices, but they were both linear systems and they were complex linear systems. So the Hungarian mathematician von Neumann recognized that all of this can be nicely coded by a Hilbert space. But a state of a quantum mechanical particle is not represented by a point in the Hilbert space. So you have to wait for a while. So I consider a vector in Hilbert space. Now I multiply it with just a phase. This is another vector in the Hilbert space, because if I take the norm, the phase cancels, and since this was an element of the Hilbert space, its norm was 1, so the norm of this is also 1. So this is also a vector in Hilbert space, but it's a different vector. Okay? Now comes the rule, easy to state, but hard to digest, that two vectors, one which is A, other one which is A multiplied by a phase, they represent the same physical state. And this is called a ray in Hilbert space. So a quantum mechanical space is represented by a ray in Hilbert space, and that is called projective Hilbert space. Okay? This is the mathematics of quantum mechanics. And I will illustrate it. How much? 5-10 minutes I have? Or you should ask them. If you're tired, we can stop right away, okay? I'll tell you what the simplest quantum mechanical system looks like. And that is at the basis of all this talk about quantum computation, quantum cryptography. So the simplest quantum mechanical system must have at least two complex dimensions. If there's only one, then there is nothing, because the only thing you can do to A is multiplied by the phase, but that's the same state. So a one-dimensional complex Hilbert space represents just one physical state, and that's uninteresting. Nothing can happen in this world. Time cannot change it, and if nothing changes, there's nothing to describe, story is finished. So the simplest quantum mechanical system that is non-trivial is two-dimensional complex Hilbert space. And now comes complications. that if A is one vector, B is another vector, I can form a C which is alpha A plus beta B. But the magnitude of this has to be 1. The magnitudes of those are already 1. Therefore, you get not yet. So now, just as we introduced unit vectors, Ix, Iy, I will introduce basis vectors called 0, 1 in such a way that 0, 1 is, this is an orthogonal basis. So I can have a state like this. This is certainly a vector space, vector in the Hilbert space, if its norm is 1, so alpha square plus beta square equal to 1. So how many parameters do we have? Alpha was complex, 2 real numbers. Beta was complex, 2 real numbers, 4, but one condition, so that leads to 3 real parameters. But I forgot to impose this condition because I don't want a point in the Hilbert space, but I want a point in the projective Hilbert space, which means that a state with alpha e to the I phi plus beta e to the I phi is the same physical state, different vector in the projective Hilbert space, but the same physical state, which means that there is one parameter, one real parameter, which has no physical significance. You can throw it away. So you must reduce the number of parameters because of this condition by 1, and you get 2 real parameters. And this is the simplest quantum mechanical system described by 2 real parameters, and this is best understood in terms of what is called a Bloch sphere. Since there are 2 real parameters, there are actually 2 angles. So you can think of every physical state now as a point on the sphere. You give it latitude and longitude, and you specify a quantum mechanical state. Okay? So the collection of all physical states is a sphere. And you see its topology is non-trivial. It's not a plane, it's a sphere. Why is a sphere topologically different from a plane? In a plane, if I draw parallel lines, they can never meet. But in a sphere, I can draw infinitely many parallel lines and they'll meet. So this is called non-Euclidean geometry, because Euclid's postulate about parallels doesn't hold for this space. And that was the major contribution of Riemann, who described these spaces, which also plays a big role in general theory of relativity. So you can choose a convention so that this is your point, and here it is 1, and then everywhere else it looks of this form. Now, these are all mathematics. Where does physics come in? Physics comes in the following way. If I take this matrix and act it on this state, I get the same state back. If I act it on this, I get 0, 0, 0, minus 1. I get 0, minus 1. I don't get the same state, but I get it multiplied by a number. These are called eigenstates, and that number is called the eigenvalue. Mathematics, very simple. 2 by 2 matrices. Now, quantum mechanics, this is sometimes given the name Z, and we say these are the eigenstates of Z. Now, just as in classical mechanics, position, momentum were properties which you could measure. In quantum mechanics, the properties are objects like this. So you can make a measurement of Z. If you make a measurement of Z on this state, which I can identify with 0, then I get eigenvalue 1. If it acts on this state, which I can call 1, then eigenvalue is minus 1. So we say the value of Z upon measurement is 1 in the first case and minus 1 in the second. So this is a rule which quantum mechanics founders built up. I'm just stating it for you. In classical mechanics, I can measure any property on any state. So in quantum mechanics, I will try to measure Z on this state. This is not an eigenstate. If it were only this, I would have got the value 1. If it were only that, I would get minus 1. But this is superposition. The superposition of classically opposite properties is what defines quantum mechanics. So what do you get if you measure Z? Not at all obvious, right? So the rule is you will get 1 with probability alpha square and minus 1 with probability beta square, which of course is simply 1 minus alpha. Dramatic change. Quantum mechanics, when I measure a property, if I carefully design the experiment, I can get definite outcomes. Quantum mechanics, no matter how carefully you build your apparatus, you will not get a definite outcome. You will get outcomes with some probability. You can never predict if I measure Z in that state, will I get 0 or will I get 1? And this is called the indeterministic nature of quantum mechanics. Probabilistic. Everything is probabilistic. Some people don't like it. Einstein didn't like it. He said things like, I don't believe God plays dice, The irony is that God plays dice all the time with our lives. Okay? I don't say with 100% confidence whether I'll be alive after taking a walk along Sayajira Road. So, this is, if you assume there is a God, he is playing dice with people's lives all the time. Whether you become a prince or a pauper, or you become beautiful or not beautiful, there is no certainty. Life is full of uncertainty. So I don't know why Einstein felt so uncomfortable. And in fact, if I were in Einstein's position, I would have welcomed it. If somebody said, "Why are you looking so ugly?" I say, "It's not in my hands. It's a dice that was thrown, so go ask that person. You will have no responsibilities in life. You can lead a very comfortable life, putting the blame on whosoever you want." That's quantum mechanics. Now, originally I thought I will tell you how this gets applied, but it's very late. But at least I've described to you what the mathematical formulation of quantum mechanics is, what are states in quantum mechanics, and what are measurements in quantum mechanics. From this follows things like uncertainty principle, etc., etc. Everything follows. That's why I say, if somebody forces me to give a one-line definition of quantum mechanics, I would say it is that theory where there is superposition of states. Opposites, you can form a superposition. If one state is me being on the left side, another being on the right side, quantum mechanics allows superpositions which are neither left nor right. You can form a superposition of Sonia Gandhi and Mahatma Gandhi, obviously two opposites, at least to me, and the quantum world that would be allowed. And the properties, all this, we are still trying to digest because it's very counterintuitive, and you can build up all kinds of paradoxes like this Schrodinger's cat, things like that. And sometimes I try to explain to my cat what all this Schrodinger's cat is, and he can't talk, but the look that he gives is one of absolute disgust. Okay, so I'll stop here. If you have some questions, you can still ask me. Otherwise, I'll leave it to Amoga to conclude this. So again, Amoga will have to do my relaying. Of course, I can make it a little easier. I'll come down. Huh? Sorry?
For 2 years, research papers will come out that they claim the room temperature superconductor.
There was a research paper saying room temperature superconductors.
Who?
Room temperatures.
Yeah. I told you. The claims. They claim it, but you just can't claim it. It should be reproducible. That's what makes science. Okay? Unlike cooking, like I can never reproduce the quality of dosa my family makes. But that doesn't mean their claims are false because I can eat and. But in science, if somebody says room temperature superconductor, there are many tests that you find. The problem with these claims, in fact, he has a very Indian sounding name, Ranga, Ranga Dias. Okay? And nobody could reproduce it. And some people found counter-example. So it went away. Now it's come back. So the claim may be right, but it has to be established. The point is, nobody has come up till now with any reason of principle why superconductors cannot exist at room temperature. Okay? It's not an impossibility. It's not like somebody saying you can't travel faster than velocity of light. People claim they're traveling faster than velocity of light also. So this is not ruled out by any principle. It's a question of verifying it, and it's very difficult because you have to produce samples which are very, very pure. So when you synthesize the samples, it's not pure and uniform. Somewhere there will be a little glob which behaves like a superconductor. Somewhere else it doesn't. So if somebody else tries to do it, they will miss that glob, they will miss that superconductor. So one has to keep an open mind. And in science, it's very important that you develop an ability to assess. When somebody says superconductor, do you just believe it, or you try to read it and say what other people say, etc. And I have somewhat of a socially relevant message here. There are many claims and counterclaims about climate. Some people say humans are causing it, some say they don't. But how are ordinary people to make sense of it? So we have to slowly build up the awareness of people as to what is climate. Most people don't even understand what evaporation is. And in most Indian families, if they're men, they don't even know where to boil water. Okay? So we have to build up concepts like evaporation, condensation, what will greenhouse gases do. There is some simple science in them, but details are always very complicated. My main message is everybody should be empowered to assess on their own. They can't do it all the way, but at least they should do it to some extent. Superconductivity, room conductors, the stakes are very, very high. But if you find a room temperature superconductor and you patent it, Shah Rukh Khan's wealth will look like peanuts.
So last class we had talked about quantum theory of electromagnetism. Quantum theory of electromagnetism and even in quartz there's some color theory. So yeah, quantum chromato something. So when we go to quantum gravitation, we see that everything has to be conserved. Like the colors have to be conserved, charges have to be conserved. So what
But nobody has been able to go to a quantum theory of gravitation. Okay? And this may be a conceptual problem, this could be a technical problem, we don't know that. And again, different people will claim different things, and it's technically very hard. And the main reason is that in gravitation, even things like time become dynamical. Okay? Whereas in all these other theories, like quantum electromagnetism, quantum chromodynamics, time is like more or less what it is in classical physics. So conceptually, it's a much easier problem. We don't know what quantum gravity is. Now some people are even claiming that gravity should not be quantized at all. Remember, I gave an argument as to why electromagnetism had to be quantized, because if you didn't, by precisely measuring the electric and magnetic fields of a charge, you could deduce precisely its position and momentum, and that would violate the uncertainty principle. There is no such argument for gravitation. And this is because in electrodynamics, the ratio of charge to mass can be anything. But in gravitation, the analogous quantity is the ratio of gravitational to inertial mass, and that is fixed to be 1. Okay? So we cannot extend arguments that were given earlier for even the necessity for quantizing gravity. So everybody is struggling, very difficult, and what adds to the difficulty is, in the case of quantum electrodynamics, in the end, what clinched the issue was that if you look at the hydrogen atom, the 2s half and 2p half, which were predicted to be degenerate, same energy by Dirac theory, are actually slightly split. And explaining that led to the breakthrough of quantum. But quantum gravity, we have no such experimental guidance. Okay? It's a very, very difficult problem, but someday we should know, is gravity really quantized or not? So I can't answer your question. I hope all of you had fun with these two lectures, and at least some aspects of quantum mechanics have been clarified. And even if each one of you feels that your understanding of quantum mechanics has progressed even this much, I would consider my job to have been done. Okay.
So there are no more questions will come to. No more questions from this side. So on behalf of Cosmos and IIA, I thank the department and university for giving us an opportunity to have Professor Haridas here, and I also thank you for agreeing to come here and give these two lectures. I hope you all enjoyed it. You can, one or two of you can just give us a brief feedback.
Yeah, exactly.
One or two paragraphs of feedback.
That would also help me.
One or two. I look forward to that. One or two
Yeah.
of you. If you can send, that would be nice. So
Yeah.
that note,
And if you can also say in what way things could have been improved, maybe the choice of topics, or the way it was explained. Did you want it more technical, less technical? Less technical would have been very difficult. More technical. For example, this qubit, in some sense, that could have been the first lecture, but then straight away I would have to go into Hilbert spaces, and I didn't want to do that. Okay.
yeah, on that note, we will conclude this lecture series. Thank you all, and thanks to the department and everyone who supported, and I thank the chairperson, everyone. Thank you all.
And thank you for organizing the things,
Thank you.
and you're doing a real service. And keep it up.
Thank you. Thank you all. See you next time for the next lecture on a different topic.